All right, yeah, thank you everyone. Thank you for the invitation. I'm Gokul Ravi. I'm an assistant professor at the University of Michigan. So until last year, I was a postdoc at the university at Chicago. So some of the stuff I'm going to talk about is stuff which I initially done when I was a postdoc over there, and some of the work I'm doing now continues to be in collaboration with Fred Chong's group over there and others. Okay, so my background before I got into quantum as a postdoc was in classical computer architecture. So in some sense, all my research focuses on hybrid quantum classical computing. Of course, one could argue that all of quantum is hybrid quantum classical, but specifically, I am interested uh, in things where there is some non-trivial effort being done on the classical side of things. This could be like pre-processing before the quantum computation, or co-processing, or post-processing, right? So most of the stuff I'm going to talk about is pre-processing. If time permits, I will briefly touch upon some of my post-processing work. Yeah, some of the work I'm not talking about today are like the co-processing stuff I do in terms of building, like, for example, cryogenic decoders for quantum error correction and so on. If folks are interested in that, I'm happy to talk about that offline. I was already talking a bunch about that during lunch. So classical pre-processing support. So some of this was already discussed by Norm, so that's great. I don't have to like go into the details. And exactly like what he had said earlier, we have applications, we want to like send the smallest portion of the application to the quantum device, because the quantum device is, even in the sort of the fault tolerant regime, it's still like going to have errors, or the cost of mitigating these errors is going to be pretty high. And of course, it's just expensive in general, right? So you want to really send to the quantum device truly the portion of the application which is beyond whatever is the best classical compute you have. Maybe that's a laptop, desktop, or the best supercomputer in the world, right? So what do we want to do on the classical side? It can be a combination of great compilers, domain software, classical simulators, and more. I'm not going to talk about compilers or domain software, though I think, especially I would love to like use more domain software and find how to integrate that to the quantum device. Right now, these two are kind of independent. They either run on software and get results from that, or on the quantum device. Right? I think integrating this is an important area of future research. So I'm mainly going to talk about simulators. Within that, of course, there are many different forms of classical simulators. Now earlier spoke about these sparse simulations and briefly mentioned tensor networks as well. So I've mostly focused on Clifford simulation and near Cliffords. Very recently, we have started looking at these match gate based simulations as well, but that is like super recent, and I'm not really going to get into that. What I would like to say is that I think all of these kinds of simulations are important. Now you could imagine that maybe you could have like some higher wrapper around this to identify which simulator is the best for a particular application. That also is a hard problem, but I think that can be done. I think it will be even more interesting if somehow we can make these simulators interact well with each other. For example, if I can do something with Clifford simulation first, because it'll be like super easy to do, then maybe some stuff on near Clifford, and then maybe pass it to something like a tensor network simulator, which would be more computationally expensive, but which can, of course, achieve more accuracy than some of these earlier methods. Right, of course. So I'm hoping that, with folks over here and others, this is something we can work on in the future. So mostly I'm going to be talking about classical simulation support for VQA. I was going to give some introduction on VQA, but we have heard this a bunch of times. So yes, this is an ansatz, and this is the kind of problem we're trying to solve. Okay, so the one thing I would like to point out is that, of course, we want to find this kind of a ground state, but the search space is noisy because of even today's noisy devices and even in the future. And there are a bunch of like error mitigation techniques that we need, and these can be like mitigating decoherence, gate error, transient errors, measurement errors, and so on. There's of course been a wealth of research in this space. I myself have worked on a bunch of these areas, which again I will not be discussing today, but if anyone is interested, happy to discuss later, or feel free to check out these works. I'm mainly going to be talking about good initialization, which again was motivated earlier. I'm going to talk about this Kafka work first, and then go into this Clapton work, which sort of builds on top of Kafka. Okay, so the key idea here is exploiting the classical simulability of Clifford quantum circuits. The Boltzmann-Nil theorem states that a quantum circuit which can be classically simulated efficiently in nearly in polynomial time, nearly linear. If it has only Clifford gates and only you have like classical measurements. So if you take an ansatz which looks something like this, so just some background, this is like a hardware efficient ansatz which is suitable to run on noisy quantum devices. We haven't really looked at like at least in this work, like UC, CSD kind of answers and so on. So here the idea is that the skeleton of this quantum circuit, which is sort of remains the same across all executions, it just happens to be the C0 gate over here. All of these other purple gates are the tunable quantum gates, right? So now you can imagine that in typical VQA, all of these tunable gates are going to take some arbitrary value between 0 and 2 pi. And this, of course, becomes a classically intractable circuit if you go to high enough number of qubits, right? On the other hand, if you're restricting these gates to be only multiples of pi by 2, then each of these gates become Clifford. And then you have a Clifford circuit, which can be, like I mentioned, easily classically simulated to any number of qubits. For example, we have run experiments with like 5,000 plus qubits in just like under a minute. And even I think that a lot of that minute was just spent in some overheads in the software itself. So the idea behind, typical VQE, what you would be doing is that you would be tuning all of these angles and you're trying to find the ground state. And this is a continuous search process, right? Because at some level, you can achieve any angle, any rotational angle with this, and you're following some kind of a gradient. So what Kafka does is that because it only works with Clifford, because it's a classical simulation technique, it only allows these gates to be these Clifford gates, right? Which means that it has now changed added this classical pre-processing step where you're doing a discrete search now, because of course, because these angles are only multiples of pi by 2, this becomes a discrete search. So you're searching through these discrete points and you're trying to find the best initial point to begin this VQA application, right? Now, you could argue that the best Clifford point, which I find over here, doesn't necessarily have to be the best starting point for the application. That is true. This is a heuristic. The idea is that if this energy is low enough, we hope that it has high overlap with the ground state. And we see this often to be true most of the time. So of course, to do this, we would need a good discrete search algorithm, your typical VQA optimizers, which are your SPSA or your implicit filter and many others, which many of you have worked on, aren't directly suitable to this problem because this has to be a discrete search. So initially, we had done some work using a Bayesian optimization technique, which is super accurate, but it is like very slow. It grows, the cost grows very quickly in the number of parameters. So until like 20 qubits, it can find the best Clifford state very quickly. But beyond that, the scaling is extremely poor. So I'm not really going to go into the details. Again, happy to talk offline. So recently we moved this to a genetic algorithm, which is not as good. It's not as accurate because it's kind of a pseudo random search, but it can be very easily parallelized. If you have a lot of small, what we call like wimpy cores, easily you can run like different genes of this population in parallel and very quickly find again this best green point, which is the best Clifford state to initialize this problem. This essentially is the Kafka idea. I'll just quickly run through some results before I get into some work beyond this. So this is just an example of lithium hydride, small molecule. We're trying to find the potential energy. And so you see the ground state, the exact energy over here in the dashed line. You have the Hartree-Fock initialization as a point of comparison. This is the Kafka initialization. Now, I should note that this is kind of an extreme case, which is why it makes for a good example where the Kafka initialization is almost perfect to begin with. This is, of course, not true all the time. But you can see sort of the extreme capability when you go beyond traditional initialization techniques, right? So you can see here that, again, I don't want to really go into the numbers. It's not very useful, but you can see clearly that we're able to like converge to the accurate much faster than the original case. And this is not surprising at all because the kinds of initial states we can achieve with using these Cliffords is going to be a superposition of just bit strings, which you'll be using with like the Hartree-Fock state. Okay, so, and this is like your dissociation energy curve, which is usually what you want to construct in these kind of problems. And you can see that the Kafka. So here the blue line is the Hartree-Fock based initialization, the green line is the Kafka initialization, and the orange line is the exact which you want to achieve. So you can see that the green line is always equal to or better. And this trend is usually the case that there is usually this gap in the middle, whereas both at the beginning and the end, you have like very high accuracy from Kafka, whereas the Hartree Fock continues to diverge further away. Now, I'm not a chemist, so I don't want to necessarily get into why this has to be the case, but we think this has to do with as the molecule, whatever the atoms move further away, there is like less forces on these electrons, and then maybe they have like equal probability of being in the upspin or downspin at the same time. Again, now chemists could tell me I'm completely wrong, possible, but this is of course how we convince ourselves as to why we see this effect all the time. Okay, so this of course is a very small molecule. This result is just to show that we could go to even larger molecules because again, nothing is stopping us in the Clifford simulation itself. Again, we do get like a lot of poly strings, so which of course requires more parallel compute, but this is not really stopping us because again, it's not exponentially, because the terms can grow pretty quickly, but the simulation cost of each in only the Clifford space is trivial. Right, so we have tested, though in the original paper, we went only until like around 40 qubits, again, limited by the Bayesian optimization. More recently, we have been able to like verify initialization for like even these 120 qubit systems. These are mainly for spin chains, again, because the number of terms don't increase as quickly. But in general, of course, we are able to achieve pretty high initialization accuracy, much more than Hartree-Fock. And using our current method, which for the stabilizer, the Clifford simulation, it uses STIM, and we use this genetic algorithm, we are able to do like these 100 plus spin models initialization in less than 1 hour. For molecules around 50 qubits, which of course has more terms, we ended up taking around 10 hours. This of course this was not on a laptop, but this was pretty limited compute on the cloud. And in general, the takeaway is that, of course, there is going to be this kind of a gap in many situations because clearly the green line, if it matches the orange line, then there is no quantum advantage at all, right? So there has to be some gap. But in general, we have seen that there is pretty good, there's a good point of initialization. Okay, so, sorry, I'm going the wrong way. Similarly, we have done some work on specifically optimizing this for Ising Hamiltonians, which I'm not really going to get into. We have some very recent work in exploring this for excited states as well, which again, not too much to discuss. This is very early work, but we find that even for excited states, we can use this Kafka approach to find a good initial point, which again is not surprising because we're just doing the same thing, right? So there are methods to model like a BQE kind of approach for excited states, and similarly, you can do the same finding these Clifford states over there. So recently, we also demonstrated this on an academic trapped ion quantum device. So where the full BQA was run on the quantum device itself with and without Kafka initialization. So the blue line over here, you can see that it reaches or it sort of touches the exact energy much faster than the orange one, which of course is what you expect over here. This is again a very small system. There's a lot of noise, but that is a lot to do with the system itself. This is a trapped ion machine from Duke, which is like, I think it was 8 qubits maybe. And so usually we see that, which again is just a case of the kind of devices we have today, that the initialization is really good, but after that, the device can't really do much to improve over this because of the amount of noise we have. Right, and the folks at Duke whom we worked with, they managed to build this entire framework of how, of course, it's much more than just Kafka, but it's about like how you can build this kind of a interaction between like Qiskit or any like kind of a high-level tool, software tool and the hardware device, and you can integrate libraries like this. Okay, so all right, so that's mainly about Kafka. Now I want to discuss a few more things beyond that. So first, at the point of Kafka is of course, yes.
Oh. Quick question before you move on. So why is the yellow curve, even in the simulation that you had a couple of slides ago, why is the energy increasing?
Why is the energy increasing initially?
Yeah, in the blue, yeah, in this one.
Well, okay, so this is a couple of things. So one is, it's just basically the optimizer itself, that your optimizer initially, if it is kind of the state it finds like a local minimum, right? So it tries to like jump around slowly, then it feels that it has to become more aggressive. So it goes aggressive, then it jumps, and that takes it away. And also the effect of noise itself. There is a significant effect of noise. And this is noisy simulation, by the way. So you see the effect of noise taking it away. And like I said, there's the noise itself can become on the real devices. Also, you have like transient noise and stuff like that. So many different reasons for why it. So in general, a heuristic is if you are starting from a better point, you are going to like converge better. Again, I won't read too much into this. First of all, is a very small system. This was, I think, approximated to like a 6-qubit system, and the noise in the system is really high. So I would say that the simulation results we see are in some sense more useful. It's a proof of concept that we are able to run on device. Okay, so this is I think where it gets. Of course, all the Clifford stuff is nice. But it's all stuff you can run on a laptop, so we don't really need a HPC cluster, right? So I think it really gets interesting when we start thinking about going to like this Kafka-ish or near Clifford simulation. So in this example, again, this is for very small systems, just H2 and lithium hydride. What we did was we found this best Kafka ansatz, which is just purely Clifford. We thought we'll add a bunch of T gates to this ansatz, right? T gates, of course, because it's easy to like see how your computational cost scales with each T gate. So here, again, this is hydrogen, so it's like a super simple system. But just adding like a single T gate, you can see that most of the gap between the green line and the orange line is being covered, right? So which is great, but again, very simple system. Similarly, in the case of lithium hydride, adding just 4 T gates again is able to significantly reduce the gap between the green line and the orange line, right? So, but this, of course, is not something which is easy to scale up, because when you go to like a much more complex system, if you have like, if I can run like 50 to 100 T gates along with my Cliffords on a supercomputer, on a pretty powerful computer, so it's hard to like identify where to put these T gates, right? Because if I'm trying to create arbitrary angles, like say pi by 6, it's not like I just put one T gate somewhere and it's going to give me my accurate angles, right? Because if you actually think about like decomposing like rotational angles to Clifford plus T, which we often do in the in fault tolerance, usually you get like these sequences of HST, HT, and so on. Right? So and therefore it becomes a very hard problem if you're just trying to use Clifford plus T and trying to like there are just too many combinations, and at least it needs a much better classical optimizer, like a discrete optimizer than what we're using. Maybe some reinforcement learning I think could be useful, but we haven't like explored that. But what I think is more probable is using these kind of other near Clifford methods. I think this was brought up even in the earlier talk today about like these operator back propagation. So the idea is that you have some observables that you want to you want to get some expectation value. You can like sort of propagate this backwards through the circuit, and if your circuit itself happens to be for every like non-Clifford gate in the circuit, you are creating more of these poly terms, and you can sort of truncate some of these terms if you based on some error bound which you're comfortable with. And so within some total number of poly terms which you're comfortable, you can calculate the expectation, right? So this, of course, is not something which I'm proposing. There has been prior work in this space. I just took this figure from this paper over here, not necessarily the work which we are following. There has recently been an IBM tool on this operator back propagation, and so we are trying to use that to go into the near Clifford regimes. And the key idea here is that with Kafka, or this Kafka style approach, what we can do is we can sort of keep our circuit in the near Clifford regime, and then we can use a method like this to simulate that efficient, right? So it's a combination of sort of this application level tool and an efficient circuit level simulator, right? So, and yeah, I'm very interested to see how this kind of a method, this Clifford plus near Clifford method, could combine with some of the sparse slash tensor simulation, which Nam discussed earlier. Okay, how much more time do I have? Do I have 5 minutes maybe? So, all right. So what we have found so far is this kind of this Kafka, this Clifford state, or a near. Assume that the next work is successful as well. So we find a good near Clifford state, right? But the question is, this is all ideally we are finding this good state noise free, but now we have to put this state on a quantum device, right? So sometimes the noise on your device, not sometimes, almost often the case that your noise is going to be fairly biased. So which means that the state that we found to be ideal, to be very good, ideally noise-free might not be as good on the device, right? So as an example, maybe Kafka might produce many noise-free states which are equivalent in the noise-free domain, but some of them might be more noise robust than others depending on their circuit structure. And similarly, there could be the case that maybe there is a suboptimal noise-free Clifford state, which maybe doesn't achieve the best energy noise-free, but it might actually perform better on the device, right? So none of this is achievable purely through Kafka because Kafka is only searching in the noise-free domain. So what we instead thought was we want to therefore find the best Kafka initial state on the quantum device, right? So what we recently did was that we are creating a depolarizing noise model which is representative of the device noise. Now, of course, this is not like extremely accurate, but it's a start. Now, this depolarizing noise just means that we are getting the single qubit and two qubit error rate probabilities. And in our case, we just got these numbers from IBM, right? So we create a depolarizing noise model with this. We add this to the Clifford circuit itself. So now, again, classically using classical simulation, we are using a discrete search process where we are finding the best Clifford state in the presence of this noise, right? So of course, this adds some cost because now we need to do multiple shots because this means depolarizing noise. So it's going to like stochastically create different instances. Again, a lot more cost. Each shot itself is easily classically simulable, but the number of shots keeps increasing, right? So, but of course, it's still easy to simulate. So we were able to run. I think we went up to like 30 qubits, and we were able to do it with fairly simple hardware. One of the ways we want to expand this is, of course, to go even with better noise models. So we want to go beyond, maybe identify like better Clifford or Pauli noise models beyond just depolarizing and integrate that with this Kafka search process. And also we want to maybe simplify the effect of noise on this hardware by using stuff like Pauli twirling. This again, ongoing work in pretty early stage. Another step at which we expanded this work was now we know this kind of a good quantum state in the presence of noise. So we wondered, can we actually transform the Hamiltonian itself such that the ground state of the Hamiltonian occurs in a noise-free or a less noisy region, right? So I'm just going to illustrate this with this example over here. So let's say that in this example, the noise is sort of increasing from left to right. So let's say that the noise-free VQA is what you see in this green line. It has its ground state over here, which is energy, the energy you're trying to find, this ideal energy at ground state. And maybe the Kafka-like method gave you the square over here, which is like this energy of minus 0.9. So now when we implement this on the device, so of course we are starting with the Kafka state. So we would have ended up with this blue square over here, which is an energy of like minus 0.5. And if we did some VQ, maybe we ended up with minus 0.6, right? Because the effect of noise is significant. The dash line is high over here. So you aren't able to really go close to the ground state. On the other hand, let's say that somehow we transform this problem, that is, we flipped it around on the x-axis. So this is basically like just a basis state change for this Hamiltonian. So here you can see that now the ground state is occurring on this side where there is low noise. This, of course, doesn't make any difference to my green line because it's all in the noise-free domain. Again, I found this Kafka state, the green square over here. But now when I put this square on the device, this blue square, produces much better energy compared to what you see over here, right? Because now I've moved the problem to a less noisy region. And therefore, then when I tune my VQA, I find much better energy, this minus 0.9, than the minus 0.6 you saw over there. So this is great. But the question is, how do I know how to do this transformation, right? Because there is more than one way to do this. And so this Clapton work, which we published recently, and in fact, it will be appearing officially next year, but it's already on archive, does this. What it does is it does many different Clifford Hamiltonian transformations, which can all be done in polynomial time. We don't know the optimal transformation, of course, but what we can do is we can try different transformations and see with which transformation does this Kafka state, which is blue square, achieve the lowest energy in the noise, which is representative of the device, right? So for example, if I had tried this one and this one, I would choose this because here the blue square is much lower energy than this one. Now, one way to do this, of course, would be to take the Kafka state and keep doing transformations and put it on the device. But this would mean the device is in the loop and it's going to become very expensive. But instead, what we can do is the same thing I described earlier, where we can have a noise, like a Clifford noise model of the device, which again, the simple one will be depolarizing, but maybe you can do, we are hoping to do better. And then we do this iterative process of Hamiltonian transformation to find the transformation which produces the equivalent of this blue square. This goes into like how we do it at the circuit level. I don't want to really get into details considering the time. But I'll just say that this is again proven to be very effective. I'll just maybe just mention one of these figures. So here you can, what you're seeing here is, if you look at this one over here, you see the Kafka line. So the Kafka found the initial state without any knowledge of noise. The noisy Kafka incorporated the noise using like a depolarizing model. So it produced a better initial state. And this is the Clapton method, which is also doing the Hamiltonian transformation. And it produces an even better initial state. After this, we run the VQA. And again, in all of these scenarios, there wasn't much we could improve given the noise of the device, but you can see other scenarios where there is a trend going downwards, right? So, and we actually evaluated this on the device as well. I won't get into again the details, but you can see on the actual hardware, the star over here represents the final energy which was found, and you can see that the Clapton energy is much better than what the other ones found. And in general, again, we went up to like, I believe, 12 to 15 qubits. You were able to achieve much better VQA benefits. Okay, so I think I'll stop here because I'm already reasonably over time. But I just want to like quickly say that we have also done non-VQA work using Cliffords. We have used Clifford circuits to do like compiler pass optimizations, because in some sense you can test your optimizations on Clifford circuits. So I'll just show this one interesting graph where it shows that what you see, I'll just maybe use two of these lines. So the red line over here is, the green line over here is some arbitrary quantum circuit. The red line is the Cliffordized version of that circuit, which could mean many things. But the most simplest way is remove all the non-Clifford gates, right? And this is like compiled for an IBM style device where I have like these, your circuit structure remains the same, right? Because if I have like, if I have like C0 gates and rotational gates, I remove some rotational gates of my C0s are all Clifford, right? So because of my structure of the circuit remaining the same, the effect of noise is very similar between the Clifford circuit and the original circuit. So you can see actually how much these things hold, the trend holds across like different compiler optimizations, right? So, and so if we know that therefore the best fidelity was produced, we know with the red line over here, that means we can use that for the actual quantum devices. And the reason why we know the red line is because we can run the Clifford circuit on a classical computer as well, right? We don't know this green line to begin with because we don't know the correct answer for the green circuit. So anyway, so like this, we have used this for both using for compiler pass optimization and also some stuff which I could have never got done in time for device optimization, cloud resource management, and so on. Okay, so I'll stop there and just quickly show on slide that is hiring in quantum. So if you're interested in faculty positions, so please consider applying. Okay, thank you.
Question for the speaker? Yeah.
So I was wondering, do you know how deep a circuit you need to prepare these Kafka states of the hardware? And is there an effort to minimize that as well so that you don't lose coherence by just having to prepare the classically chosen initial state?
Yeah, it's a great question. So yes, so we have found that, so we have not looked at it from like a sort of a theoretical perspective because my group and the people I work with aren't necessarily theorists. But we have seen that once we found like a good state, right? So we found the good Clifford state in a noise-free fashion, but we are able to like when we just like sort of go through the circuit, we are able to like find some redundancies and reduce the circuit considerably. So, and I'm sure there might be like an optimal depth reduction, which is possible, which would be like much more useful, right? So yes, we have done some of it. We have seen it's possible, and potentially there is room. Good question. Yes.
When you do the Clifford simulation, so as you said, you have a specific a small number of gate sets. Have you considered maybe doing a symbolic simulation, and then getting at the end a result where you can just immediately find the solution and not use the genetic optimizer?
Okay, so first of all, I'll just say that I don't know much about symbolic simulation. So, but maybe I'll generalize it. So like I said, so we, in the original method, we have to stick to Clifford gates, right? So we have to somehow do any search process such that it sticks to Clifford gates, right? And once we have some Clifford-based quantum state, we can evaluate the energy for that state. And so based on that, now, there is no reason for us to limit ourselves to the Bayesian optimization of genetic algorithm. If there are better methods, we can use better methods, right? So, but yes, our only restriction is we have to stick in the original work to Clifford's, and maybe in the other work, more recent work I was talking about, we are looking at near Clifford's, right? Where again, there is some restriction. But on top of that, what optimizer you want to use is totally up to, like, we have only tried two and we've got good results, but by no means are they optimal. There's one more question somewhere. Yes.
I had a question on one of your simulations of like a chemistry simulations.
Mm-hmm.
When you have the bond length being really large, like the Kafka is doing really good.
Yeah.
That's what I remember. But like my question is like when the bond length is really long, what does Kafka actually gives you the circuit? Like I mean, I kind of sort of assume that in that case there wouldn't be much of an entanglement, I guess. So does it just give you a bunch of Hadamars, or like I mean, are there CNATs also like in the picture? For example, A equals like 2.5 in this case, or
we definitely get a bunch of CNARs as well. Now, again, it's could relate to the old question that we have not like tried to optimize this. So it could be possible that if we like take the circuit that we get, we could optimize it, and maybe some of these gates get removed, right? So I am sort of telling this purely from a computation perspective, where we started with a skeleton, we optimized this, and we got some state, right? So we have not now taken that state and say, like try to compress it into the most simplest version of it possible, right? So, but at least our intuition is that it's basically giving us like an equal superposition of many like bit strings basically, and it's just that the reason why that is like super accurate, like we get this very high accuracy, is because in fact we think that the electrons are having this equal at that kind of higher bond length, has equal possibility of being this upspin or downspin, right? So again, I could be totally wrong, but that's every problem we have seen, we have observed that we get like really high accuracy in those domains, right? So, but it's possible that we could, maybe many of the CNRs could get it, right? So,
quick question there. So what is the circuit depth there for the green one then?
what is the circuit depth?
Yeah, in terms of the gate.
Well, okay, the way we have currently, the unoptimized version will have the same, whatever is the circuit depth of the answer, right? Because
oh, so you're not adding layers as you go in your.
No. So what we do is, so what we do is, let's say this was my ansatz, right? Again, this is a very simple answer.
You're only changing the one to the gate here.
Exactly,
Oh,
right?
okay.
But I guess, but there is a possibility that we could compress it more, right? So we are doing this to some extent, that we find a Clifford state, and then we have done like some basic methods to compress it more. But we are not ever adding anything further.
Gotcha.
So we are still assuming that. So just like for novel VQA, you need to know a good way to choose an answers. We are not doing anything more than that.
Genetic algorithm.
Oh, the genetic algorithm is only playing around with these angles. So it has nothing to do with the CNOT itself. Yeah, sure, clarify.
So, like developing some sort of like adaptive technique where you're adding layer and layer after. Is there some downside to that?
It is possible. I don't think there's any downside. So yeah, I think it's totally possible. I think for the initial work, it did not matter because we were totally in the noise-free regime. So in some sense, we didn't care because lower depth, higher depth is less relevant to us. But now that we have started exploring noisy versions of this with these depolarizing noise, I think it is possible that we could do it in that fashion. We have had some discussions with like the adapt folks like Sofia Economos group, and in fact, they were interested in like maybe starting from a Kafka state in their work. So yeah, I think all of that is possible. It's not exactly clear like how much benefit you will get more, but yeah, it's possible.
Thank you, speaker.
All right, thank you so much.